Welcome to the deep dive. Today we're diving into the world of light, how it interacts with matter and all that. We've got excerpts from two really cool physics textbooks to guide us. Atoms and Light, Interactions by John Dodd, and Optics, The Science of Light by Paul Ewart. And to help us unpack all this, we've got expert speaker joining us today.
Hey, it's great to be here. Light, right? It's something we experience constantly, but its true nature has really puzzled some brilliant minds for, centuries.
It's true. Dodd even mentions this critic from the early 1800s who compared the wave theory of light to, get this, wild phantoms. Wild!
Yeah, and you know what? Those early debates were actually super important because they really laid the groundwork for how we understand light today. And what's really cool is that even with all the complexities of quantum physics, classical physics still gives us a pretty accurate way to describe how light behaves, especially how it interacts with charged particles and atoms.
That's good to hear, because honestly, quantum physics sometimes makes my head spin a little. But speaking of mind-bending concepts, Dodd dives into some pretty intense equations to describe those electromagnetic fields, the ones from accelerating charges. One thing that really stood out to me was this idea of the virtual position of a charge. Sounds kind of sci-fi, right? Can you break that down for us?
Okay, so imagine you're looking up at a star in the night sky, right? You're actually seeing light that left that star thousands of years ago.
Oh, yeah. It's like we're looking back in time.
Exactly. And because light takes time to travel, the light that we're seeing isn't telling us where that star is right now, but where it was way back then. The virtual position of a charge is kind of like that.
Sorry.
So because information can't travel faster than the speed of light, the electric field at a point in space doesn't instantly know where the charge is right now. Instead, it responds to where the charge would be if it had just kept moving at a constant speed, from a slightly earlier moment, and that's its virtual position.
So it's like the electric field is reacting to a delayed image of the charge, based on where it used to be. It's like the universe has a tiny bit of lag.
That's a great way to put it. And getting this whole virtual position thing is really important for understanding why accelerating charges give off energy, why they radiate. It's like the charge changes direction, and that creates a sort of kink in the electric field. And that kink, that's what spreads out as an electromagnetic wave. In other words, light.
Okay, that makes sense. So we've got these electric fields, we've got waves, but how do we measure how strong light is? What does that even mean for light to be strong? I mean, in my reading, I kept coming across words like intensity, energy density, even something called the pointing vector. Can you help connect those dots for us?
Yeah, so think about a garden hose, right? The intensity of the light is like how much water is flowing out of that hose. So higher intensity means brighter light. Energy density, that's a little different. That's more like the pressure of the water. It's like how concentrated the energy is in the light.
Okay, so a laser pointer would have high intensity, but a dim light bulb could actually have higher energy density if you focused it down to a tiny point.
Exactly, you got it. Now the pointing vector, that's like if you're trying to figure out which way the water from the hose is actually spraying. It tells you how much energy is flowing in what direction.
So if intensity is like the brightness of the light, the pointing vector tells us where that brightness is going.
Exactly. And these ideas get even more interesting when we start talking about things like standing waves. That's where you have two waves, and they're the same frequency, but they're traveling in opposite directions.
Right, like when you shake a rope that's tied down at one end and you get those peaks and valleys that seem to stay still.
Yeah, exactly. And in those cases, you might have high energy density in some spots, right? Like a lot of pressure in that field. But the pointing vector, that would average out to zero because the energy is just going back and forth.
Wow, that's wild. It's like a crowded dance floor, but no one's actually going anywhere. Okay, so we've got these tools to describe light's energy, how it moves, but things get really interesting when we look at light interacting with matter, right? Dodd mentions this thing called the Compton effect. Sounds like it was a pretty big deal in the physics world.
Oh yeah, it definitely shook things up. The Compton effect basically showed that light can transfer some of its momentum to a charged particle, like an electron. Almost like they're playing a tiny game of billiards.
Wait, hold on. Are we saying light is acting like a particle now? I thought we were in the world of waves.
Good question. That gets right to the heart of the mysteries of light, really. See, the classical wave model, it really struggled to explain the Compton effect, because when light bounces off an electron, the scattered light, its wavelength actually increases, meaning it loses some energy. And the classical wave model just couldn't explain why that wavelength would change.
So how did they explain it? Did they have to completely ditch the wave model?
Well, not completely, But they did have to make some pretty big changes. What they found is that how much the wavelength shifted depended on the angle of scattering, just like if two particles collided. And that's what led to this idea of photons, these packets of light energy, each one carrying a specific momentum. It's like light can act like a wave in a stream of particles depending on how we're looking at it.
Mind-blowing. That's what's so fascinating and kind of confusing about light. This dual nature that just doesn't make sense if you think about our everyday experiences.
It's true. And even physicists who study this stuff all the time still find it pretty mind-boggling. Ewert talks about how we can take a single beam of light and break it down into all these component frequencies. It's kind of like separating the ingredients of some really complicated recipe. And then we can actually put them back together. And by doing that, we can learn all sorts of things about where that light has been.
Wow, so it's like there's a secret code embedded within the light itself. That reminds me of something I read about Fourier transforms. It seems like understanding how complex waves are made up of these simpler ones is really important to unlocking those secrets of light.
You got it. Imagine a musical chord. It's this complex sound, right? But if you have the right tools, you can break that chord down into its individual notes, its fundamental frequencies. And Fourier transforms, they let us do something really similar with light. We can express any complex waveform, it doesn't matter how messy it is, as a sum of simpler sine and cosine waves. Each one has its own frequency, its own amplitude, and phase.
So it's like taking apart a rainbow and seeing all the individual colors that make it up.
Another great analogy. And just like knowing the recipe tells you about how a dish will taste, knowing the Fourier decomposition of a light wave, it tells us about its own unique properties and behaviors.
This is already blowing my mind. It's like we're learning a whole new language to decode the language of light itself.
And, these tools, like these Fourier transforms we've been talking about, they become even more powerful when we start thinking about how light interacts with, the basic building blocks of matter, atoms.
Right. And both Dodd and Ewert really get into the weeds on this, like diving deep into the quantum world of atoms and how they interact with light. It's amazing to me how Dodd emphasizes that the energy levels of atoms are quantized. It's like they can only handle very specific portions of energy, kind of like picky eaters at a buffet.
Exactly. Atoms can only absorb or emit light at very, very specific frequencies. And those frequencies, they match up with the differences in energy between those allowed energy levels. It's like each atom has its own, special set of musical notes that it can play.
And that's what gives us those beautiful line spectra, right? It's like each element has its own unique fingerprint, its own barcode, but made of light.
Precisely. Each element sings its own, unique song.
Yeah.
And Ewert, he takes this idea even further and brings up this idea of finesse in optical instruments.
Finesse? That sounds fancy. Is that like a measure of how sensitive and precise an instrument is?
Exactly. So imagine you're trying to listen to this really faint melody, right?
Yeah.
And it's being played on an instrument that's super far away. A high finesse instrument that'd be like having this super sensitive microphone that could pick out those delicate little notes and all that noise. In optics, finesse tells us how well an instrument can resolve these super fine spectral lines, those unique fingerprints of each element that we were just talking about.
So higher finesse means we get a sharper view of the atomic world, like having a super-powered magnifying glass, but for the spectrum of light.
You got it. And speaking of amazing optical instruments, Ewert's book, it goes into some really, really ingenious devices. One that really caught my eye was this thing called the Fabry-Perot interferometer. It's basically like this resonant cavity for light, kind of like an echo chamber, but just for specific wavelengths.
Okay, now I'm intrigued. How's that work?
So picture two mirrors, but they're super reflective and they're facing each other. So they basically form a sort of light trap. Light can bounce back and forth between these mirrors, but, and this is the cool part, only certain wavelengths that perfectly match that distance between the mirrors, the ones that resonate with the cavity, only those build up in intensity.
So it's like it filters the light, letting only certain colors through and blocking all the others.
Exactly. And the really cool part is that if we adjust the distance between the mirrors really, really precisely, we can fine-tune the interferometer to pick out and analyze incredibly specific wavelengths of light.
It's like a tuning fork, but for light. And it's wild to think that this whole idea of resonance, which shows up so elegantly in the Fabry-Perot interferometer, has all these applications that go way beyond just analyzing light. I remember reading about how it's used in lasers, for example.
You're totally right. Lasers, they totally rely on this amazing interplay between light and matter. Basically, you need more atoms in an excited state than in their ground state.
Yeah.
Like a bunch of kids who've had way too much sugar, right? And to get a laser to work, you got to amplify the light that's emitted by those excited atoms. And that's where the Fabry-Perot cavity comes in. It's like that echo chamber that amplifies only that very specific wavelength of light that resonates within it. That's what creates that super intense focused beam that we know as laser light.
So the Fabry-Perot cavity, it's like the heart of the laser, keeping the beat for that coherent beam of light. This is all so cool. But while Ewert is diving deep into all the practical stuff about these optical instruments, Dodd and atoms and light, he takes us on a bit more of a, philosophical detour. He asks this question that has been bugging thinkers forever: what actually is light?
It's a question as old as time.
Right.
And even with all the incredible advancements we've made, all our intricate models and theories, we still don't have a perfect answer. Dodd, he suggests that maybe instead of getting stuck on defining the true essence of light, we should focus on the stuff we can observe. Like, how does light actually behave? How well do our models predict its behavior? All that.
So it's like saying, hey, we may not know exactly what's going on inside a clock, but if it tells time accurately, that's good enough, at least for now.
Exactly. It's a very practical way to think about it. Science, at its core, is really about building these models that can accurately describe and predict what's happening in the world around us, even if those models don't perfectly capture, the ultimate reality of the situation.
Right. It's a good reminder that science is always evolving, always searching for these deeper truths.
Totally. And we've made amazing progress in understanding light, uncovering all its secrets, but there's always more to learn. It's a journey that never really ends, which honestly makes it all the more exciting.
It's amazing to think about all this, all these mind-boggling things about light and how much we've learned, but how do we actually see these quantum effects happening? We can't actually look at a photon or watch wave-particle duality in action, can we?
That's a great question. You're right, we can't directly see these quantum things happening, but what we can see is how they affect stuff. A lot of our understanding comes from how light interacts with matter, especially our detectors.
So let's talk about detectors. What's actually going on when light hits one of those things? It's like those tiny photons are knocking on a sensor or something.
That's a pretty good way to think about it. A really important process in lots of light detectors is something called the photoelectric effect. It's kind of like the opposite of what we were talking about before, with atoms giving off those specific frequencies of light.
Right. Like Einstein explained, it's like a photon hits an atom with enough energy and boom, it knocks an electron loose. And then that creates a current, which we can measure.
Exactly. And for a while, this seemed like, proof that light was made of particles. But here's the cool part. Even the photoelectric effect, which seems like it should be all about particles, we can actually describe it using quantum mechanics. And quantum mechanics, that brings in both the wave stuff and the particle stuff.
So even when we're just talking about how we detect light, that wave-particle duality, it's still there. You just can't escape it.
It's like it's woven into the fabric of light. And it reminds us that all our everyday ways of thinking about the world, like things we see with waves on a lake or throwing a baseball, those ideas, they don't really translate to this quantum world.
It really makes you realize how much more there is to learn. It makes me think about something else Dodd mentioned. He called it photoelectric counting statistics. Sounds intense. What's that all about?
It's really interesting. It's all about how there's this randomness built into how we detect light. Even if you've got a perfectly stable light source, it's not changing at all, when each photon hits your detector, that's random. We can't predict it precisely.
So even with a steady beam, it's like those photons are all racing each other, and you never know exactly when each one is going to cross the finish line.
Yeah, that's a great way to put it. And in the same way you might analyze how long it takes a bunch of runners to finish a race, to learn about their speeds and how they run, we can analyze those photon arrival times, and they can actually reveal hidden patterns and tell us about the light source itself.
Okay, so how do we make sense of all this randomness? Are there rules to this photon race?
Oh, there definitely are. One of the big ones is called the Poisson distribution. Basically, it's a statistical tool, and it describes random independent events. And turns out that if you have a perfectly coherent light source, like a laser, those photon arrivals, they follow that Poisson distribution really well.
So if we made a chart of how many photons hit the detector over time, it would match up with this Poisson pattern.
Yeah, you got it. But, and this is really cool, when you start looking at light sources that aren't perfectly coherent, like the light from a regular light bulb, the Poisson distribution, it doesn't really fit anymore.
Right, because that kind of light is messy. It's a mix of different wavelengths all jumbled up.
Exactly. So with those kinds of light sources, those incoherent ones, the photon arrivals, they tend to bunch together more. You're more likely to get a bunch of photons showing up at once than you would expect if it was truly random.
So it's like those photons are more social, they want to arrive at the party in a big group, not all spaced out.
I like that. It's a great way to think about it.
Mhm.
That bunching effect, that's actually a big clue that the light is incoherent. It's another way that, even in this seemingly random data from the detector, there's all this hidden information about the light itself just waiting for us to find it.
That's incredible. It's like the universe is sending us these secret messages, but they're hidden in these tiny little photons. So are there any more surprises hiding in this photon data?
Oh, absolutely. One of the most mind-blowing things scientists have found is that there are actually these things called non-classical light sources. And they do this thing called anti-bunching. It's like the opposite of what we were just talking about. The photons are actually less likely to arrive together than you'd expect just by random chance.
Anti-bunching. It's like they're actively avoiding each other. How is that even possible?
It just goes to show you how weird and wonderful this quantum world is. That kind of behavior, it's a signature of those non-classical light sources, the ones where the photons are entangled. That means they have this special connection that can influence each other, even if they're separated by, huge distances.
It's like they're doing a synchronized dance, but they're on opposite sides of the stage.
Yes, exactly. And that anti-bunching, it's opened up this whole new world of possibilities in quantum optics. Things like quantum computers and ultra-secure communication networks. It's really incredible.
Wow, it's amazing how something that seems so simple, like, just counting how many times a light detector clicks, can lead us to such profound understanding, not just of light itself, but of the entire universe. Expert speaker, this deep dive has been amazing. I feel like I have a totally new appreciation for something we take for granted every single day.
My pleasure. And remember, listeners, next time you flip on a light switch or look up at the stars, think about all the amazing things we've talked about. That intricate dance of the photons, echoes of ancient light, and all the mysteries that quantum mechanics is revealing. There's a whole universe of wonder hidden within each and every beam of light.
That's right. And for you, our listeners, we hope you've enjoyed this journey into the world of light. Keep those minds curious, and we'll see you on our next deep dive.